Hello students. So in last class we are discussed about isotopic peak. So up to here we are discussed now the metastable ion and their peaks. So here this is a metastable, as the name says, it is a metastable ions. That means after the bombarding in the principle you observe. So we are bombarding in the source. So ion source, in the ion source we are bombarding with the ion, the compound with a free moving electron or other way of, yes, here some ion source. That means here compounds are bombarded with a ion or a other process here. So here what happens, the formation of ion takes place in the ion source, and then what happens, the ions which are formed in the ion source, they are unstable because they are bombarded here, and then they are their stability of the compound becomes low here. And in that cases, what happens in the metastable ion state means the ions which are produced in the ion source. So here the ion source are produced here by the bombarding or any other technique. Then what happens while traveling in this circular path? So it must travel in the circular path here, and then it collects here. But what happens while traveling in the circular path, the ion start to decompose. That means because of the instability of the ion, the compounds start to decompose here in the path only. That means, for example, in the ESA, electrostatic analyzer, what happens? The compound A, it gives the compound with ion form of A. Then, while moving from ESA to Na, that means magnetic analyzer, what happens? The A which converts into another ion, that means it decomposes it into another ion, that's A plus B, and then it collects in the collector. So in the analyzer, what happens? It shows two state of decomposition, A and here AB. So this what happens, the collector which collect the AB, but the production of the ion is A plus, and in the collector it collects A plus. That means AB, a different compound because of the decomposition, and this is what we call metastable. That means it is not stable, complete stable, or not complete unstable. So it is in between. That means while moving in the circular path, so it shows the two or more different compounds. That means it's life cycle of decomposing compounds here. So this is what we call the metastable state. So here the lifetime of an ion formed during the fragmentation in an ion source is so small. That means its lifetime. That means the ions which are formed in the decomposition or in the fragmentation is very small and undergoes decomposition. That means the decomposition of that compound is a uh, here the ion source is small, that means fragmentation or lifetime is very small, so it start to decompose from beginning of the circular path to the ending of the circular path. So in the beginning we get one compound, means at the end we will get another compound. So this is what we call metastable state. From the first point you can understand. So what is the metastable state? The metastable state, they are the ion undergo decomposition with a short lifetime period. So that means in the circular path only they decomposes, and in one analyzer or in the first slit they shows one ion, and at the end they show different ion. So this is what we call the metastable ion state. And then the ion resulting from decomposition between ion source region and the magnetic analyzer called metastable, as I explained. So the ions resulting from decomposition between, so here what happened, the decomposition normally takes place at the ion source, and then it collects at the collector. So that's a common, in common. But here what happens, the decomposition between the first, here the decomposition takes place here, and while moving to here, it decomposition goes on, and then here one compound is decomposed into A plus ion, and while coming to the magnetic analyzer, it gives a different compound. This is A plus B. I gave the name only just for an example. So this is what we call metastable ion state. So these ions appears in the mass spectrum as a broad peak. So here in the yes here you can see here in this picture you can see the metastable ion peaks. That means it shows the broad peaks. That means these all are sharp peaks. That means sharp lines we have. Okay, these all are stable ion state. That means they are stable. But here you can see this is a broad. So that means the V shape is broad at here. This is because of metastable state. That means the reason is they are undergo decomposes here. So because of this reason, it shows the broad peaks. So here you can see the metastable ion, that is 104.3. So that means 180 is the uh, first one. That means in the here ESA, that means electrostatic analyzer, the atomic number is 180, mass number is 180. So while moving to the magnetic analyzer, the compound with the atomic mass number 137. That means here to here, that means from the electrostatic analyzer to the magnetic analyzer, it changes or it decomposes its nature. So this is what we call the metastable ion state. The peaks useful in the studying of the mechanism of the fragmentation. So this is also useful for the study of mechanism, and then from the position of the parent M plus and daughter M2 plus, the position of the metastable ion can be calculated. That means the position, that means the stability time or stability rate we can understand by the broad peaks. That means the length and width of the broad peaks we can understand. So here we have the equation here. This is the equation. That means the decomposition M1, that is the parental ion, and it gives M2 and M. That means it is the compound with the decomposition point here. So it undergo decomposition as like this. Okay, and this is the calculation, the metastable state calculation. We have the formula. So just go through this, and this is enough. And this is about the metastable state. And then interpretation of mass spectrum. Now we have discussed different peaks. Normally in the mass spectra, we have different type of peaks, that means parental and isotopic peak, and then base peak. And now we have the interpretation. That means we have to just imagine we have one, yes, we have one mass spectrum like this or like this. Then we have to understand or interpret this graph, and we will get the information. To interpret this graph, we must know some of the rules and some of the points. So just go through that points, and then you can easily understand how to interpret the graph of mass spectra. So the interpretation of mass spectrum or mass spectra. So here mass spectrum is the graph here. And first point, very important point, the each compound gives the characteristic series of fragments called the fragmentation pattern. So here what happens, the fragmentation pattern gives the, they have their own fragmentation pattern, like our fingerprint. That means the different compounds have their own fragmentation. For example, carbonyl compound, uh, nitrogen compound, oxygen compound. So these all compounds have their own fingerprinting pattern. That means fragmentation pattern. So if they have the carbonyl group, that means C double bond O group, means they fragments in different way. Okay, compared to nitrate groups or nitrogen groups. So they have a different type of fragmentation. They have a characteristic series of fragmentation in a compound. Okay, the mass spectrum of each compound is its fingerprint. Okay, so the mass spectrum of each compound is fingerprint, as I explained, and then the different peaks are identified and tabulated. So the different peaks are identified. That means the peaks are identified on the basis of their size, and then their mass number. So this is the different peaks are identified and tabulated here. And then the fragmentation pattern is to be determined. That means fragmentation patterns are determined here. The following general rules are observed. That means to determine the pattern of fragmentation, some of the rules or observation of the rules we must do here. They are the very important rules to understand the fragmentation. And here, the first one is the fragmentation process involves in homolytic or heterolytic cleavage of a single bond. So what happens? The first thing, as I said, after the bombarding of a compound M, we are bombarding with the electron, just imagine. Okay, and then what happens? It gives the ion, parental ion. After this, what happens? As I said, they undergo fragmentation, and this fragmentation have two different type of cleavage. These two are not a unknown word for you. So there's a homolytic and heterolytic cleavages. So what is homolytic cleavage and heterolytic cleavage? So here, for example, we have a compound of A and A, or A or B, anything. So homolytic means have the shared electron. They are equally shared between. That means this bond is because of the covalent bond. That means sharing of electron. After the breakage of bond, what happens? They divide. That means they took their own electron. Okay. So what happens? It's homolytic. So here if you have the two electron, so one electron is taken by the A and one is by A. So here it is homolytically divided. Heterolytic means what? Here, for example, A and B we have means if the B is much more stronger than A, then what happens? Both the electrons are taken by this one compound, the B, and this A get the charge. So this is what we call heterolytic cleavage. So homolytic cleavage means what? Here two shared electrons are taken by their own parent compound, and then that is called homolytic. They are equally divided. Then the bonded electrons are equally shared between the two compound or a two atom. So this is called homolytic cleavage. The heterolytic cleavage, the sharing of electron is not homolytic. That means they are taken by one atom. So this is called heterolytic cleavage. So this is first type. And then the cleavage reaction may followed by rearrangement, elimination, and other chemical reaction. So the cleavage here, the cleavage of reaction followed by it may be rearrangement or elimination or a chemical reaction. This any one of the process it occurs in the cleavage process. Okay. And third one, fragmentation corresponding to single bond cleavage will occur with a little or no reverse activation energy. So here what happens, the fragmentation in some cases it the single bond cleavage will occur. Okay, the bond will break here, and in some cases what happens, they show some of the reverse activation. That means here the bond is break, for example here, and it gives M from the parental M plus ion, it gives M1, smaller M1 and M2. Just imagine here. Okay, one is stable compound and one is another ion. But what happens here? The parental ion which gives the daughter ions, this daughter ion, sometime what happens, they combine again and it gives the parental compound only. So this is what we call reverse reaction. So if they have the reverse reaction activation energy, some of the compound have some amount of energy, and most of them use only the parental ion gives the daughter ion. Okay, and this is what we call the reverse activation. This is called reverse activation energy, and this is the fragmentation energy. So here the fragmentation corresponding to single bond cleavage. Normally, the single bond cleavage, this will occur. So, with a little or no reverse activation energy. Okay, in constant fragmentation involving loss of stable molecule may involve reverse activation energies. That means, in the fragmentation involving loss of stable molecule may involve reverse activation energies. Thus, for a single bond cleavage, the activation energy of a fragmentation will be approximated by. That means we can calculate the activation energy. So here the activation energy of cleavage or fragmentation we can calculate by a formula. There's a delta HA. Delta HA means the energy required to activate the fragmentation, and then delta HF. So here the fragmentation, that means the energy of the product minus energy of the reactant. So that means the bonding energy of the reactant and bonding energy of the product here. So the bonding energy of reactant and bonding energy of product, that's a delta HF. So here the energy, the more the energy, remaining energy of delta HF minus delta HF of product minus delta HF of reactant. This is what we call activation. That much of energy, if we are supplied with, it gives the product or a fragmentation. So this is the calculation, simple calculation. And then to identify the compound, the following rules are used. So this is all the observation we did, and next we have to identify the compound, the following rules we must follow some rules. They are: one, first, it's very easy one, and it's very important, the nitrogen rule. So the nitrogen rule, very simple, it is very simple here. The molecule of even numbered molecular mass. The molecule with the even numbered molecular mass must contain no nitrogen. If they have the even number of molecular mass, then there is no nitrogen or an even number nitrogen. If nitrogen is present in that type of molecule, means they must have the even number of nitrogen atoms. So that means, for example, we have the 122 as a molecular mass, then it must have even numbers of nitrogen. Even 0 is the even number. So that means no nitrogen or a 2 nitrogen or a 4 nitrogen or 6 nitrogen. Only even numbers of nitrogens are present. Not 1, 3, 5. They are odd number of nitrogens. They are not possible here. If they have the even number of the molecular mass, then must have even number of nitrogen. It may be 0 or any other even number. So this is a rule, and this rule not only holds for the nitrogen and other compound atoms also we can apply here. This rule is good for all the organic compounds containing carbon, hydrogen, nitrogen, oxygen, sulfur. So this is why we are using this rule. So this is not only for nitrogen, but the name is nitrogen rule, but we can say in general, we can give the definition, the fragmentation at a single bond. If it is single bond cleavage, only this is the condition. The condition is they must have the single bond cleavage, gives an odd numbered ion fragment, and which gives odd numbered ion fragment from an even numbered molecule ion. That means if the parental ion, just see here, the parental ion have the odd number of molecular mass, then it gives the even number of fragments. So this is the parental ion. So same thing, this is the parental ion with the odd number 1, 2, 3. So 123. So is the molecular mass. It gives the odd number of parental molecular mass, and it cleavage is, that means fragment parental or daughter ion must have the even numbered molecular mass. So this is the example here, even number here. And then similarly, an even numbered ion fragment result to give a odd numbered molecule. Here I explained the parental ion with the 1, 2, 3 as the, that means 123 is an odd number, 123 molecular mass, and it gives the parent daughter ion of NO plus with a molecular mass of 30. So odd number of parental ion gives even number daughter ion. If they have the even number 122, just imagine 122 means it gives the parent daughter ion as a odd number. So this is the odd number. So this is what we call the nitrogen rule. And here we have the example. This example you can see here, NO2. That means we have one example, there is NO, there is with the 30, or another possibility is NO2 formation. That means the bond breaks here. Okay, if the bond breaks here means the compound with the at molecular mass of 46, that means NO2. This breaks here means it becomes NO2, so it is molecular mass is 46. And if the break takes place here, then the compound is this one. It's also have the molecular mass of 30, that because the parent ion has the molecular mass of 123, is the odd. So this is one example. And this example illustration, what is nitrogen rule? They ask for 3 or 4 marks question. They ask what is nitrogen rule? Explain with the example. So this is the example you have to explain, and it is very easy one. So parental ion you have to remember, and then you can easily illustrate the example. So it's very simple. And then here also the uh, m by charge ratio is 93, and then the compound, then it becomes unstable, and the formation of or removal of CO, that means carbon monoxide takes place. And then here the carbon monoxide is the E1 number here, and this is a possibility, that means this is also one possibility, and this is another possibility. That means we can expect two type of fragmentation here. So this is one possibility, and this is another possibility. Just go through the exam, there is enough for you. And then another example of nitrogen rule. So here the nitrogen rule, there is a 2,4-dinitrophenol. So here the 2,4-dinitrophenol is another example. As the name says, this is a phenol compound. Okay, phenol compound with the OH here, and NO2 in the second position, and in the fourth position we have 2 nitrogen. So what happens here? This is the example for E1 number parent ion. This is the example for odd number. This is the odd number parent ion. And here what happens after the bombardment? The fragmentation takes place like this. That means the fragmentation takes place by removal of one H plus ion, and it gives the parental ion is 184 E1 number molecular mass, and it gives odd numbered. So here it gives the odd numbered ion. So this is the odd number here, 183. So 184 is E1 number parent ion, and daughter ion has the odd number molecular mass. And then what happens? Next, it undergo a removal of carbon monoxide, and it forms the compound of with the molecular mass of 155. So this is the fragmentation. And second example, so first example for E1 odd number example, and second example is E1 number parental ion example. And here the observed peaks are as follows. That means for the observation peaks, we can easily see here in the picture, but just go through these two. That means M plus H plus, that means the remove 183, and then 155 in the second one. At the last we will get the 155. So the peaks are like this, their abundance on the base of abundance, we will get the peaks. So one in the 183, and then another peak is at the 155. Like this we will get. And just go through the example, that's enough for you. The molecular M plus appears M by mass by charge ratio 184. The fragment ions contain both nitrogen appear at odd mass number with the, which proves the validity of nitrogen rule. So here, which is the proof for nitrogen rule. The fragmentation model. So here, the fragmentation model are here. This is the fragmentation model. So in the exam, you have to write the explanation, and then you have to write the fragmentation model. You must write here also, both the cases. And then the ring rule. So this is also another easy rule here. The ring rule, to calculate the number of rings. So that means for a organic compound, if we have the organic compound, then to calculate the number of rings R, okay, we have a formula. That is W plus 1 plus Y minus X divided by 2. So here, what is W, X and Y? So here, the ring rule, that W, X, Y, Z, they are, the W means number of carbon atom and X is number of hydrogen atom, Y is number of nitrogen, and if we have the Z instead of any one compound, nitrogen or oxygen, if they are replaced, Z means they are the oxygen number. And here, the number of rings in the molecule plus the number of double bonds plus twice the number of triple bond. So the ring rule says that the number of unsaturated sides of R, that means number of unsaturated means number of double bonds in a ring, it is equal to the number of rings in the molecule, number of rings in the molecule plus number of double bonds plus twice the number of triple bonds. That means is the calculation here. Just for example, in the example or illustration, you can easily understand. Let us apply the rule of benzene. So here benzene, R is equal to W means what, number of carbon atom. How many carbon atoms we have? 6. So here instead of W, write 6. And then plus 1 and then plus Y. What is Y? Number of nitrogen. In the benzene, there is no nitrogen here. So Y is 0. So this is 0, Y is 0. And then minus 6. X is number of hydrogen atom. So 6. So totally, this 6 plus 1 minus 3 here. Minus 3 here. Right, minus 3. Why? 2, 3 is a 6. Okay. This minus 6. Sorry, minus 6 becomes minus 3 here. So 6 plus 1, 6 plus 1 minus 3. So totally it becomes 4 here. Okay. But we know the number of double bonds in the compound of benzene is only 3. So this is the benzene structure. Only we have 3 double bonds. But we got the answer 4. Thus the benzene contains 1 ring and 3 double bonds. And what is the meaning? The meaning is 4. This is because it have 3 double bonds and 1 ring. Total it becomes 4. So we have to calculate like that. So it have 3 double bonds and 1 ring. So totally it becomes 4. Okay. It is not the thing that it have 4 ring or 4 double bond, not like that. So it means it have 3 double bonds and then 1 ring. So this is the meaning here. And then let us consider diethyl ether. So diethyl ether, that is a C2H5O, C2O5. So here C2H5O and C2O, C2H5. So here what happens? R to calculate the ring. So the 4, what is 4? Number of carbon. Here it is 2 and here it is 2. It becomes 4 plus 1. Okay. And then 0. How many nitrogen we have? There is no nitrogen. So it becomes 0 here. 10. Number of hydrogen atom is 5 plus 5. It is 10. So after the calculation, we will get 0. That means hence diethyl ether contains no ring or no double bond. Here the diethyl ether structure, you know, oxygen with the C2H5 and here C2H5, same thing. Hydrogen, hydrogen, and then hydrogen and hydrogen. The same structure is here. So there is no double bonds. So the meaning of 0 means what? There is no ring and there is no double bond. So this is the ring rule illustration. So in this, we have to remember this formula, and then what is W and what is X, what is Y, what is Z. You have to remember this. Okay. And after the calculation, while writing, don't write there is 4 double bonds. Not like that. The meaning If it have the 4 means what? 3 double bonds and then 1 ring. Total it becomes 4. Okay. So you have to write like this or calculate like this. And then let us consider 2,4 dinitrophenol. So with the nitrogen, here we have the example with the nitrogen, and hence here I will go to the result only. Okay. So here X, Y, Z. Sorry, X means 4 number of carbon atom. Sorry, X is for number of hydrogen here. So here 3 hydrogen and here 1 hydrogen 4. W is 6. W means number of carbon, here only 6, and then Y is 2. That means number of nitrogen. Here nitrogen is 1, but we have 2 NO2 molecule. So nitrogen is 2, and then this enough. Y and Z. So Z is 5. That means here we have the 4 oxygen, and here one is, there's a 4 plus 1, there's a 5 oxygen. Okay. And how to calculate the same thing? After the calculation, we will get 6. Okay. So how to illustrate this 6? The 6 means they have 5 double bonds, 1 ring. The meaning is they have 5 double bond and 1 ring. So this is the calculation. And then you can calculate the double bond ring of benzophenol and just calculate this one, solve this one. Then you can easily understand. So these all are the example for the ring rule. And then even electron rule. So next we have the even electron rule. In the even electron rule, an even electron species will not normally break into two odd electron species because the total energy of this product mixture would be too high. It's very simple. Okay, it's very simple. Even electron species, they do not undergo break into two odd electron species. That means if they have the even electron species, then they do not undergo odd electron species. In the example, you can easily understand. For example, this is the even electron. Okay. In the odd electron, if they are after the fragmentation, they use the two odd means there is the homolytic cleavage, and then in that case, both the daughter ion with a 1 plus charge and another one with a free radical. So both the daughter fragments are unstable because it is charged and it is with the one active free radical. Then the stability of the compound becomes very low. Okay, there becomes very unstable here because both are charged. So it is not possible, their stability is very low, they are not possible to stay in this state. So if they have the even electron, they undergo heterolytic cleavage. So that means one will get the charge and another one will get the neutral. So here it is charged, that means it is unstable, but here the carbon get the neutral, so sorry, C, compound C, which is neutral, so its stability is high. So in that case, it is possible. But here both have the charge and radical. In this case, what happens? Their stability becomes very low. So they undergo this type. That is the second one. This type of cleavage, not this type. So because of their stability. So this is even electron. If they have the even electron species, then they undergo even cleavage, not odd cleavage. And then we have, if they have the odd number means number of parental ion, then it undergo odd even. Okay. Then here, but the radical being odd, so here the molecule leaving a radical ion as a product. So both the, in this case, the one compound will get both radical and charge. So this is possible. The radical ions can also degrade into radical and an ion. That means this is also possible. That means odd, even, and odd. In this case, one which get the radical, and then get the positive charge. Or here like this, A plus with the odd number of parental ion, and it gives the odd and even. So this we can see here in the example. There is the ester, carboxylic acid, amide, radical ions. So odd electron species can be see here the ester, the formation of ester. So this is one example here, the radical with radical and also with the positive charge. And then carboxylic acid, here also it have one radical and with a positive charge. This is possible. So these all are the example here. So here what happens, they are undergo these three type of cleavage. So that means odd even, even odd, odd even. So this is about the odd number parent ion. This is about even number parent ion. Here it gives only even as a daughter product. So this is what we call even electron rule. So even electron rule means the even number parent ion which undergo only even cleavage. Okay. Odd number, they may undergo odd even odd. Okay. So this can be possible. So this is the type of fragmentation. To illustrate or to identify the fragmentation, we must know the parental ion molecular mass. So this is about the rules. Next we have the mass spectra of some compound. And this is also very important. And these three rules also important. They all are 3 or 4 mass questions. All these questions are very important. And then we have the mass spectra of some compound. So I will explain this in the next class. Thank you.